Welcome back to our video module on dynamics. On the left, I've written 3 scenarios where we're using pulleys to accelerate some mass or applying some force. In scenario 1, right here, what we're doing is we're using the pulley simply to change the direction of the applied force. So we're pulling to the left. If you're the block, you feel the force going to the right. In scenario 2, we're using the pulley to amplify the force. So the cart's going to feel some sort of amplification of the force. And in scenario 3, we're using the pulley to amplify the distance that the cart is going to move. Historically, you've probably looked at pulley systems in static environments. Today, we're going to look at them in a dynamic environment to try to understand how they influence our equations of motion. That said, let's get started. Let's make a little grid here so we know what we're looking at. For each of these scenarios, I'm going to look at a couple characteristics and I'm going to try to understand what's happening. The first scenario is probably something that you're somewhat familiar with. The first scenario is we want to compare the distance that this point A travels compared with point C. So point A corresponds with the applied force location, point C with the location of the cart. So what we can say is the x position of A divided by the x position of C, and because we don't have to worry about directions, let's just look at the magnitudes of those. And if we look at that in scenario 1, that's easy, right? It's just 1. In scenario 2, point A, if it goes 2 inches, the cart will go 1 inch. That should be a review on basic pulleys. So the distance A over distance C is simply 2. And in a corresponding manner, if point A goes 1 inch, point C will go 2 inches. So in this case, it's 1/2. Now, if this ratio right here tells us the distance between the 2 points, we know that that happens over the same time. So we know that it also is the magnitude of the velocity of A over C, which is also equal to, we'll put it on the left in, I don't know, teal, is equal to the magnitude of the acceleration of A over the acceleration of C. So this is useful information if you're given the motion. You're told that point A is going to move at 5 meters per second. You know that the cart is going to move at 2.5 meters per second. But we might also be interested in the forces and the motion caused by those forces in this system. Now let's quickly draw a free body diagram for the cart in scenario 1. In gray are the normal vertical forces that we're not going to look at, but horizontally, notice I've put the tension because I don't yet know what this tension is. Now, of course, you and I intuitively know it's going to be F, but let's do this a little bit more rigorously. And the way to do it more rigorously is then draw a free body diagram of the pulley system. Let's take a look at what that looks like. Here I've drawn what I know. I know that the applied force on this top part of the pulley is F. And since the tension in the pulley is consistent, in other words, it's a massless pulley, we also know that the tension in this part of the rope is also F. By inference, we know if we're going to balance those forces, the pulley isn't moving. We know that the tension in this cable is 2F. Now notice this rope right here, this rope right here, and this rope right here, they're the same rope, which means that the forces within that are going to be the same. Our final step is to write the equations of motion now that we have our free body diagram finished. And that's going to be, as always, we'll just write this up here because we always do the sum of the forces equals the mass times acceleration. And since we're only dealing in horizontal components, I'm not going to write everything as vectors. So let's write the equation of motion for the cart. We see that it's T, which is the force or the tension in the rope, equals the mass times acceleration. We know T equals F, so we know F equals ma, or if you wanted to write acceleration by itself, we'd say acceleration equals F over m. Great, so in scenario 1 we have some really useful information. We know the ratio of the velocities of the applied force to the cart. We know the equations of motion that correlate the applied force with the acceleration of the cart, and from that we could also find its position and its velocity as functions of time. The next step is to try this with scenario 2. Let's start by writing our free body diagram for the cart. And interestingly, in this case, it's exactly the same as scenario 1. Now let's try the free body diagram of the pulley. Go ahead and put the video on pause and see if you can navigate this on your own. We'll regroup in a couple seconds. So hopefully you ended up with something like this in teal. First, we know that the upper tension is the applied force. That's right here. That's this area. That's the applied force right there. We secondly know that the tension in this rope has to be constant, so we know the force down here is also F, and that would correspond to this area right here. Finally, we know our massless pulley, sum of the forces must go to 0, so this component is now 2F, which means that the tension in the rope is equal to 2F. Let's go ahead and use that up here when we say T. The tension is equals the mass times the acceleration of the cart. That's our equation of motion here. And we know that the tension is double the force. Remember, these are both one component. So 2F equals ma. And if we wanted to know the acceleration of the cart, so the tricks we used here are knowing that the tension in the rope is constant, same as in scenario 1, and that the tension in the rope on this free body diagram is the same as the applied tension right here. So T equals 2F. Interestingly, we also see that the acceleration of the cart is now twice as much as it was in scenario 1. And that one can intuitively understand is we're applying, with our applied force, we're doubling the effective applied force on the cart, so the cart's going to accelerate twice as fast. Finally, let's do the free body diagram and equations of motion for scenario 3. Go ahead and put the video on pause and see if you can get these on your own. We'll rejoin in a couple seconds to compare our notes. Hopefully you ended up with something like this. And the way we got this was we know that the applied force is on the pulley. The sum of the forces is going to equal to 0, which means this tension plus this tension is going to counteract this force, and we know that they're equal. So half of the force goes to the top one, half goes to the bottom one. Now we see that this rope right here corresponds to this tension from our free body, or from our drawing. So we know that the tension equals F over 2. We use that here. And we find that the acceleration is half as much under the same applied force as what happened with scenario 1. So this is really interesting. Let's take a look at scenario 3 where we're applying the force. If I apply a force at A, I see that my cart accelerates at half the amount that it would have if I had just applied it here in scenario 1. Now that's really interesting because let's say that instead of applying some force at A, I instead apply some acceleration. Now, I don't care about the force, I'm just going to do some acceleration. I know that the acceleration of A divided by the acceleration of C is 1/2. Right? So I apply some acceleration at A and I find that that's equal to the acceleration of C over 2. Which means that if I apply, a 1 foot per second squared at A, the acceleration at C is 2 feet per second squared. I have this amplification in acceleration if I simply accelerate point A. But if I apply a force, I see that the acceleration cuts in half. This is one of the interesting aspects of dynamic use of pulleys as compared to static use of pulleys. One final characteristic of these pulleys that is worth noting is that in this system there is no energy added or subtracted, which means that the work done at A, which would be force of A times the distance of A, is going to equal the work at C, which is the force of C times the distance of C, and this is true for all of these equations. Another way to say it is if energy is conserved and it's happening over the same time, we also know power is conserved. And by power conservation, we know that the force applied at A times the velocity of A is equal to the force applied at C times the velocity of C. A good way to interpret this is if between A and C we double the force, that means that the velocity will get cut in half. Or if we apply a certain velocity at A and we know that the velocity at C is doubled, we know that the force at C must be cut in half. In summary, we have two perspectives we can take when looking at pulley systems in dynamics. The first one is we take a look at its ratio of positions. This is more the kinematic side where we're told the position or the velocity or the acceleration as a function of time. The second type of problem or type of situation we might find ourselves in is over here where we're given a force and we need to find the mass times acceleration. And in that case, we draw our free body diagram. Then what we did is we set the forces equal to each other. In this case, it was tension and force. Over here, it was T and 2F. Here, it was T and F over 2. And then we use our equations of motion to identify the acceleration of whatever we're looking for. I hope this revisitation of pulleys has given you a better feel of how they work in the dynamics world. We'll explore them more in our next video module.